Hello, everyone. I'm Max Al-Hasso, and as mentioned, I'm a research engineer at Quantum Dice. And today I'm going to be talking to you about our orbit probabilistic processor. So first, I'm going to have to change both at the same time. Okay. Thank you. A bit about the company. So Quantum Dice is a spin-out from the University of Oxford, and we're backed by venture capital, by the UK government, and by the EU government. And we began life by producing high-speed quantum random number generators. And today, for the applications of sort of simulations and cryptography. And today we're working on applying that QRNG to accelerating randomized algorithms. So, Orbit is our probabilistic computing platform, and that begs the question, what is probabilistic computing? Usually when I talk about this topic, I have to introduce it from the start, but we've actually heard about it twice today already. First from the speaker from Basel Quantum, and then from Dr. Novoselov as well. So hot topic today. Probabilistic computing is built on a unit of information called the probabilistic bit, or the p-bit. If we're here, we're probably familiar with bits and qubits. A bit is a classical unit of information that stores the state either 0 or 1, and a qubit exists in a superposition between those two states. A probabilistic bit fluctuates between 0 and 1 with some control probability. And actually, as Dr. Novoselov mentioned earlier, this either requires quite a degree of computation expended on a classical computer, or you need to simulate it physically, which is what we're using the QRNGs for. So probabilistic computing arises from this idea of natural computing, actually from the same talk where Richard Feynman introduced quantum computing. And the idea is that you simulate like with like. So in a quantum computer, you need quantum hardware in order to simulate quantum properties. In a probabilistic computer, you need hardware that is naturally non-deterministic to simulate non-deterministic algorithms. Probabilistic computing simulates stochastic physical systems like gases or gas atoms interacting. The computation is performed by mapping problems to these physical systems and then allowing them to evolve. And in a similar way that in gas atoms, neighbors may interact with one another and cause some effect, p-bits will interact with their neighbors to determine that tunable probability. And in this way, they can work together to solve some large combinatorial problems, as we've been hearing a lot about today. Okay, so Quantum Dice, we produce photonic chips. This is the PIC, the photonically integrated chip, that we actively manufacture for those earlier mentioned applications. And this is the entropy source for our probabilistic bit, rather than simulating anything on traditional hardware. And yeah, these chips have been validated at scale. They're used in several different applications already. So, these are some examples of computational tasks that map well to probabilistic computing. First, we have the QUBO, as we've just heard a lot about. They're widespread in optimization problems, and they involve interactions of two terms, but no more than two terms. That's the quadratic in the quadratic unconstrained binary optimization. On the other side, we also have this hypergraph optimization. And the reason for separating this out is that it's actually a higher order optimization problem, so you can have more than two bodies interacting. And this becomes increasingly more difficult to solve when you have higher order terms in an optimization problem. And for many combinatorial optimization solvers, these become very difficult to embed, where you're typically used to only two terms interacting. A further application is energy-based machine learning, as things like restricted Boltzmann machines and the layers in a neural network map quite well to this sort of stochastic binary p-bit model. But today we're going to be focusing on optimization. So how does it compare to other methods that are available? So if you wanted to, specifically for heuristic optimization is what I'm referring to here. So for simulated annealing, this is a classical method for solving these QUBO problems, for example, and it's highly optimized for a subset of classical problems, but it's less scalable as it's CPU bound. And the advantages that we find there are less generalizable. In comparison, p-bits are accelerated by inherently stochastic hardware and are applicable to a broader set of problems. Quantum annealing, D-Wave, as was also just mentioned, The hardware topology actually limits the problems that can be effectively solved with this method because you have to map it to a very specific kind of graph structure in order to use those devices. In addition, there's very complex error handling if you're trying to use it at scale. In comparison to p-bits, they are more expressive. As already mentioned, you can do these higher order terms without having to bake them into some specific topology. And it operates at room temperature and is far more energy efficient. It actually also happens to be faster. For variational quantum algorithms, very promising, but they are limited at today's scale. I mean, we just heard about some very promising applications. And as I say, the usability is limited by present-day hardware. There is, in comparison to p-bits, there's a shorter route to practical scale deployment, and again, just to reiterate, room temperature, more energy efficient. You may also parallelize your algorithm, in which case you'd be using GPUs. They have high energy consumption. We hear about nuclear facilities being built to power GPUs at the moment. And they are expending a lot of that energy on deterministic hardware, trying to make randomness, so TRNGs, PRNGs, any other kind of random number generator. In comparison, probabilistic computing is orders of magnitude lower energy consumption specifically for randomized algorithms. This is specifically in that domain. Yeah, also to say that in the same way that you might export some parallelized computational task to a GPU, for a randomized algorithm, you could do the same to a probabilistic computer. You still have a central CPU that processes general computation, and then for the bit that needs to operate in the randomized algorithm, you export it to this other piece of hardware. So we're going to look at some applications, some application domains. First and foremost, combinatorial optimization. These domains include scheduling operations, telecommunications, logistics. This is what's most relevant to sort of maritime applications. Furthermore, we have AI and machine learning. These are specifically energy-based machine learning applications. We have the generative machine vision and unsupervised learning. And then finally, simulations as well, which is what these devices were built for originally, simulating complex systems, and in the near term, before quantum computers are available at large scales, we can simulate those quantum circuits as well. Okay, so next we're going to look at a couple of case studies, starting with autonomous fleet management. So the problem in consideration is the management of an autonomous fleet. And this is broken down into a series of optimization problems that are really placement, navigation, and scheduling. The probabilistic computer will then solve these problems in real time. And one important point here is that if you incrementally change the problem parameters, your solution incrementally changes with that, rather than having to restart or resolve. This is kind of the point that Dr. Novoselov was making in his presentation. It's very useful for like certain, almost like adiabatic operations. And this leads to improved utilization of resources, dynamic responsivity, and better operational planning capabilities. There we are. The next use case that we'll look at is optimizing maritime operations. And one example optimization that we've identified is crane and berth scheduling. We just heard about that in more detail. And here we would solve that in real time, and similar to before, if the problem statement itself changes based on new real-time information, the system can adapt and does not need to restart its optimizations. And this would lead to dynamic solutions, improvements in key metrics, and downstream logistics benefits. So a bit of a deep dive. If we return to the example of the fleet management. Yep. Imagine I have these points across London that I want accessible by some aerial drone. That means that I would need to station those drones within some radius from that point. In an amount of time, they can only get so far. So what I want to do is station the fewest amount of drones in order to be able to cover all these points. And you might find some optimal allocation where you only need 4 drones. The reason why we look at that problem is it's like a real-world use case of the hitting set problem, which is a higher order optimization problem, i.e. it has more than quadratic terms. So this is an example of like something that gets very complex very quick. And a recent study showed a 4 times improvement in time to solution using this method. So this is what the probabilistic computer looks like. It's a standard 2U server rack. It doesn't need any special cooling, no special environmental requirements, and it is traditional CMOS. It's CMOS plus, which is traditional CMOS plus some quantum entropy source. Also worth noting that we're currently operating with 4,096 parallel p-bits in one unit, but that's soon to be a lot more. And yeah, so kind of in conclusion, our goal is to build the platform for accelerating next generation combinatorial optimization tasks and artificial intelligence models. Thank you. We can use the rest of the time for any questions.
So thank you, Max, for sharing the insightful sections. And we'll now take a short break, and we will resume our next section at 3:45. Thank you.
Thank you.